subtract the n equals 0 term. So I just plug in 0 in for n. So I have -1 to the 0, 3 pi over 4 to the 0, over 0 factorial. So here, I subtract n equals 0 term. Understand that? Any questions so far? Yes?
How come you had to start the first one at the index of 1?
You didn't have to. If you could find the pattern when n equals 0, that's fine, but then you'd have to do a lot of exponent changing because your exponents wouldn't match up with the Maclaurin series. Right? So if you start at n equals 0, then your exponent would be 2n plus 2.
How would you know that though? How'd you, like, I'm just trying to figure out how you knew that the index had to start with 1.
Well, you don't have to start, if you wanted, you could have started with 0.
Well, like,
okay, and then you would just have to change your exponents instead of changing the index.
I just don't know how you knew that.
Because I found the pattern first, so I said, well, this should equal raised to the 2n, and now I have to figure out what my index is. So remember, I found this part first, okay, and once I did that, and I found this part because I wanted to match the Maclaurin series. So once I did that, then I see, well, what do I have to plug in to get to that first term? And n equals 1 when I plug in gets to that first term, not n equals 0.
Okay.
So sometimes it might be easier to find the pattern first before you find the index.
Okay.
Make sense?
Yeah.
Okay. Any other questions? Okay. So now I continue. So again, this one is in the form of cosine x, where x equals 3 pi over 4. Okay, so now I just take that Maclaurin series. Here 3 pi over 4 isn't replaced with x, so now I just put 3 pi over 4 into x here. So this equals cosine of 3 pi over 4. And then minus the n equals 0 term, okay? Well, here, all my exponents are raised to 0. So that's just 1. And I have 0 factorial, that's 1. So this whole thing is 1 over 1, which is just 1. So I'm just subtracting 1. And again, this is the n equals 0 term. And what is cosine of 3 pi over 4? Sorry?
Negative square root of 2 over 2.
Negative square root 2 over 2, thank you. Minus 1. And that now simplifies to negative of square root 2 plus 2 over 2. Questions? Wasn't that so much fun? You guys don't seem as excited as I am. It's not okay. Okay, so that is sum of series, all right? So again, you can find the sum of an infinite series by using our common Maclaurin series and just plugging in, all right? So now we move on to integration. So you already saw integration of functions represented as power series. Okay, we saw that in section 11.9. And so now we're going to do the same thing, except now we have more series to choose from. Okay, so we just convert this function to a series and then integrate it. All right, and so now we have more series to choose from because now we have lots of Maclaurin series. Before we just converted using power series, but now we have special types of power series called Maclaurin series. Okay, so I'm going to convert know how to integrate cosine x over x squared normally. So we can at least represent it as a power series. So I have cosine x, which is a sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial, all over x squared dx. And so now, okay, if this is over x squared, then I can just divide x to the 2n by x squared and subtract exponents, okay? Because remember, a series is just an infinite polynomial, or a power series is an infinite polynomial, so that's like writing out each term, and if I do that and I divide by each term by x squared, then that's the same as dividing this pattern by x squared, we'll get the same thing. Okay, so I'm just going to divide x to the 2n by x squared and subtract exponents. So here I have the integral of the sum from n equals 0 to infinity, negative 1 to the n. Again, I subtract exponents, I get x to the 2n minus 2 over 2n factorial dx. Any questions so far? Okay, so now I can integrate. All right, so I have c plus sum from n equals 0 to infinity. And so remember, I'm integrating with respect to x, which means negative 1 to the n is just constant. Okay, that doesn't change because it's just a constant in terms of x. So I have negative 1 to the n. Then I have x to the 2n minus 1 because I added 1 to the exponent. And then I divide by that exponent, 2n minus 1. And again, 2n factorial is also constant because it doesn't contain x, and we're integrating with respect to x here, so I just leave that as is. Any questions? Okay, so again, we don't know how to integrate sine x minus x over x, so we can at least express it as a power series here. Okay, so I'm just going to represent this function as a power series and then integrate it. So this equals, right, the integral. Now I see sine, which means I can plug in the series for sine in. So I have the sum from n equals 0 to infinity, negative 1 to the n times x to 2n plus 1 over 2n plus 1 factorial minus x over x dx. And so sometimes it's easier if we just write out the first few terms of the Maclaurin series and then we can cancel some stuff out. Okay, so that's what I'm going to do here. Again, you should memorize the first few terms of each Maclaurin series. And so sine is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot dot dot. Okay, make sure you have the dot 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 there because that tells you it's an infinite series. It goes on forever. Minus x over x. Questions? All right, so now the x and the x, negative x cancel, right? So this just gives me the integral of negative x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial and so on. Okay, and that's divided by x. So all I did was cancel out the x and the negative x in the numerator. Yes?
Why wouldn't you want to factor out an x?
Why wouldn't you want to factor on x? Where?